Oh, good morning. Welcome to Dr. Hugh Ross's Paradoxes Sunday School class. Dr. Ross is with us today, and he'll be here next week too. He's going to be talking about the general revelation and design of the universe. Continued presentation. With that, I'm going to say a short prayer, and we'll call him up here. Bow your heads, please. Almighty God, we welcome you into our classroom. We ask your blessing on our presenter and the presentation. May it be honoring and glorifying to you, Lord. May it help us in our witnessing endeavors for you. In Jesus' name, amen. Dr. Ross?
Well, welcome to all of you that are here in person and all of those that are participating through our online medium. Yes, as announced, we're continuing a series on the designs of the universe that make possible the redemption of billions of human beings. And I've actually written 7 full-length books on the fine-tuning argument for God, how everything is amazingly fine-tuned, not only to make possible our existence, but also our redemption from sin and evil. And the process we're taking is starting with the universe as a whole and actually focusing in closer and closer to home, and now we're inside our Milky Way galaxy. Last week I spoke about the black holes in the local group of galaxies. That's referring to the galaxy group of which our Milky Way is a part, and how the black holes at the centers of the galaxies and the stellar black holes in our Milky Way galaxy are all amazingly fine-tuned to make possible in this narrow window of time advanced life here on planet Earth. And I got a couple of questions after the class that I'm going to review. People are asking me, you made the point that it takes 2 neutron stars merging together to make a black hole that produces about half of the elements in the periodic table. How is it possible for 2 neutron stars to merge together? Good question. About half of the stars in our galaxy are either doubles or triples or quadruplets or 5, which means you've got 2 or 3 or 4 or 5 stars that are all orbiting one another, kind of like the planets orbit the sun in our solar system. Half of the stars find themselves with partner stars. Now, a really big star, a star that's, say, 15 times the mass of our star, the sun, will end its nuclear burning by becoming a black hole. Stars that are, say, somewhere between 3 and 8 times the mass of our star, the sun, they'll be shedding mass, and by the time they're done with their nuclear burning, they collapse and become a neutron star. The vast majority of stars are not massive enough to become a black hole or a neutron star. They wind up becoming a white dwarf. And an analogy for a white dwarf star is, think about a log that you're throwing on an open fire. That log keeps burning, and eventually the log consumes all of its fuel, but it's still hot. And so it takes time for that log to cool from, say, a bright yellow or orange color to a deep red to an infrared, and eventually the log becomes completely black or brown. Same thing's true as stars. So our star, the sun, when it finishes its nuclear burning, will end up as a white dwarf star. And it'll be quite hot at that time, about 30,000 degrees centigrade, and then it will begin to cool down and become what astronomers call a black dwarf. But the cooling time is very long. We're talking trillions of years for a white dwarf star to become a black dwarf. One reason why we know the universe isn't extremely old is we don't see any black dwarf stars. None of the white dwarf stars have had adequate time to completely cool down. Now, what is rare is for a double star system where you got 2 stars orbiting one another, where both of them are of the mass such that they end up as neutron stars. And end up in such a way that they remain together, because if you got one star that's bigger than the other, as it goes down into the neutron star phase, it could literally eject the partner star. And so it's quite rare where you get 2 stars that end up as neutron stars that are orbiting one another. And because these neutron stars are so incredibly dense, they exert a significant gravitational force on one another. And it's a theory of general relativity that tells us that two neutron stars orbiting one another will lose orbital energy. And so what happens is that the orbit gets smaller and smaller and smaller. And last week I showed you a video clip of two neutron stars that under general relativity see their orbit getting smaller and smaller. And of course they go around one another faster and faster, just like Mercury goes around the sun about 4 times faster than the Earth because it's closer to the sun. This too happens with neutron stars. And as they lose gravitational energy, eventually the stars wind up merging together. And if two neutron stars merge together, they'll become a black hole. And so that's where neutron star merging events come from. But as also mentioned last week, even though astronomers have been using their gravity wave telescopes for over 4 years now, they've seen many black hole merger events, but they've only seen 2 neutron star merging events. And we're talking about surveying the entire universe. And so we know that neutron star merging events are quite rare, and that these neutron star merging events make about half the elements in the periodic table. So for example, here's the periodic table. And what I've done with this periodic table is overlaid each element in the periodic table with a purple square. So everywhere where you see kind of a purple square, that's an element that's predominantly made by neutron star merging events. And there's 48 of them. So 48 of the 94 naturally occurring elements, 92 today because plutonium and neptunium decayed away when the Earth was just hundreds of millions of years old. But 48 of the 94 elements are what we would call elements that are manufactured predominantly in neutron star merging events. Now people asked me last week too, these elements you got in the chart here, are they entirely made by neutron star merging events? Many of them are. But for some of them, you get a small contribution from what we call core collapse supernova explosions. Because when you get a really big star undergoing a supernova collapse, it generates a huge flow of fast-moving neutrons. And it's that flow of fast-moving neutrons hitting the lighter elements that builds up these heavy elements. That's one thing you notice. Everything that's shaded purple there is towards the bigger elements as opposed to the smaller ones, because that's what's happening. You get 2 neutron stars that are merging together, and when they merge, you get this huge shower of intense neutrons, and it's that shower of neutrons striking other elements that builds up these elements that you see in the periodic table. And as I mentioned last week, 3 of these 48 elements are what we term as vital poisons. That's a term that we coined at Reasons to Believe to refer to elements in your body that if you got too little of them, you will die. If you got too much of them, you'll also die. They have to be at the just right level. I mean, one famous example is chromium. And, there are people who have, excuse me, there are people who have a chromium deficiency, and so they'll go to the health food store and they get these chromium supplement pills. However, I would encourage you, don't take too many of those pills, because if you put too much chromium in your body, it will cause serious health problems. Put a lot of chromium in your body, it'll kill you. But it's also true if you don't have adequate chromium, that also leads to serious health problems, and if you're especially deficient, it will kill you. Well, there's 22 elements in your body that are in that category. Too little, you'll die. Too much, you'll die. And if you get close, well, you might not die, but you'll have serious health consequences. 3 of those 22 elements are manufactured by neutron stars merging together to become black holes. And that would be iodine, tin, and the molybdenum. These are 3 elements that are essential for you to be able to live, and they're made by these neutron star merging events. And so one of the remarkable features of our solar system, it happened to be born in a really big cluster of stars in which one of those stars was a binary star where both stars were big. They wound up becoming neutron stars, and the neutron stars were able to merge together quickly enough that our solar system got enriched with just the right amount of these elements. And we're not just talking elements essential for life, we're also talking elements that are crucial for our advanced civilization. And so this would include things like silver, gold, platinum, so what we call the valuable metals, uranium, thorium. These are made by neutron star merging events. And so we're able to have the kind of high technology civilization that we do because we happen to be in a solar system, a planetary system, where it got just the right amount of enrichment at the right time. And it has to be fine-tuned. If our solar system formed too close to a neutron star merging event, that event would have destroyed the solar system, or at least disrupted its system of planets. And if we form too far away, then we don't get adequately enriched with these rapid process elements that we see here in the periodic table. It's also necessary that we be enriched at just the right time. And so the timing and the location both have to be crucial. And so, yeah, you can get the recording of last week if you want to see the discussion we had in black holes. You can also read a paper that got published in a peer-reviewed journal that I wrote, and it's titled Black Holes as Evidence of God's Care. Remarkable article because I happened to draw three astrophysicists, two at least of which were atheists. The only one don't know what his background was, but you get to read their reviews. Two of them wanted to reject the paper. I think they're rather offended I was connecting God with black holes, but I was able to respond, and the paper did get published. Well, where we left off a couple of weeks ago is we talked about how we live in a just right galaxy. And this is where I compared our Milky Way galaxy with every other known spiral galaxy that could possibly be a candidate for light, basically making the point that even though we can look at millions of spiral galaxies, our Milky Way galaxy is the only one that has the galactic characteristics that makes possible the existence of life in our galaxy, which means we need to change the scripts for all those Star Wars movies. It can't be a galaxy far, far away. Our galaxy is the only one we have found that could be a possible candidate. What I want to talk about today is how we live in a just right location in our Milky Way galaxy. We lived in a just right spiral arm. We live in a just right bubble along that spiral arm. And we live in a just right fluff ball within that local bubble. And so this next slide here basically shows you the location of our solar system. We're on the inside edge of the local arm. We're not right on the arm. We're kind of off center from the local arm. As you can see in this image, it's not a main spiral arm. We're basically on what's called a spur arm. And as you can see here, it's actually part of the Perseus spiral arm. The Perseus and the Sagittarius spiral arms are the two dominant spiral arms that are nearest to our solar system. But you can see branching off from the Perseus arm is what's called the local arm, and that little circle represents the position of our solar system. In fact, let me give you a little bit of a blow up here so you can see exactly where we are. And this particular image, and by the way, this is not a photograph from some telescope that went above our Milky Way galaxy and took a shot looking down. That's much too far away to pull that off. Rather, what we're seeing here is a carefully constructed map of our Milky Way galaxy by pulling together images of different parts of our Milky Way galaxy, taken at different wavelengths, across the entire electromagnetic spectrum, from long radio wavelength maps all the way to gamma ray astronomy maps. But as you look along that local arm, you notice something. What you notice is that our solar system seems to be residing in a rather vacant place along the local arm. When you look to the left of the local arm, to the right of the local arm, you look above, you look below, there's not a whole lot there, which means that our solar system is not being gravitationally disturbed by nearby massive objects. And incidentally, we're not right on the local arm. We're a little bit below that local arm and a little bit above. This is a two-dimensional image, so it really doesn't do it justice here. We're really a significant distance from the core structure of the local arm. But I think you can see in this image, there's no nearby massive star clusters. There's no nearby gaseous nebulae, nothing that would disturb the geometry and the orbits of planets in our solar system. And moreover, there's no deadly radiation source. And so you don't want to be close to what we call the maternity wards of our galaxy. So as you look at this image, wherever you see a pink spot or a big pink spot, this is a place where stars are forming. And so this is what astronomers call the maternity wards in our Milky Way galaxy, where star formation is going on. But when you got a site of star formation, a giant molecular cloud of gas and dust that's collapsing to make stars, you get these really big stars that are very bright and they burn quickly. They're also radiating deadly ultraviolet and X-ray radiation. You don't want to be around one of those things. And what's fortunate is we happen to be living in a location within our Milky Way galaxy where there are no nearby gaseous nebulae, and the nearest one isn't that big. Incidentally, we're coming into a time when you actually see that gaseous nebulae. October is a time when the Orion constellation comes up late at night. By Christmas time, it's right up there at 8 p.m. And the Orion Nebula is the one nebula, gaseous nebula, star-forming nebula, that you can actually see with the naked eye. Well, not in the Los Angeles basin, but if you get outside into a dark sky site, you can look at Orion, quite recognizable. You can see the three bright stars that are the belt stars. Then hanging down from the belt, you see three faint stars. The middle star of the sword of the Orion that's coming down from the belt, that's the Orion Nebula. There are stars there, but the nebula is actually brighter than the stars. And it's a nebula that you see with the naked eye. And so here's a Hubble Space Telescope image of the Orion Nebula. And, you can see many newborn stars there. But it's actually quite small. I mean, if you look at it through a telescope, it fills about a half moon diameter of space. So if you got a nice telescope, it can actually fill the field of the eyepiece. We're only talking about 1 moon diameter across. And it's about 1,450 light years away, so it's quite distant. And even though we got big bright stars forming there, with a lot of nasty radiation coming out, we're far enough away, it poses no risk. Now, let me contrast that with what you see in our Large Magellanic Cloud, and you can actually see this with the naked eye as well. So here we got the Orion Nebula, 1,450 light years away. The Tarantula Nebula is 163,000 light years away, and yet you can see it with the naked eye. Again, not here. You got to be in Australia, Antarctica, or New Zealand to see it. But here's an image of what is called the Tarantula Nebula. You can kind of see it's got the shape of a big spider. So, and this is typical of giant molecular clouds and spiral galaxies. But our Milky Way galaxy does not have any gaseous nebulae as big as this one. Interesting because, whoops, let me put this back in here. Come on. Here we go. Sorry about that. The Large Magellanic Cloud is about 6% the size of our Milky Way galaxy. But it's typical of small spiral galaxies and large spiral galaxies, and it is filled with these really big, giant molecular clouds. And to give you an idea of the size of this, if we were to put the Tarantula Nebula in place of the Orion Nebula, have the Orion Nebula and Tarantula Nebula trade places, when you look up at the night sky, you would see the Tarantula Nebula, and it would cover 80 moon diameters across the sky. That's how big it would be if we put it in the same location as the Orion Nebula. You say, how bright would it be? It'd be as bright as a full moon. And so, if that was the case, we wouldn't be able to do much astronomy, because you have this huge nebula up there shining so bright, filling so much of the sky, you wouldn't actually be able to see any galaxies because of the way it was illuminating the nighttime sky. The Tarantula Nebula is also filled with giant stars that are radiating that vicinity of the Large Magellanic Cloud with deadly radiation. And here's an example of where I put the Orion Nebula side by side with the Tarantula Nebula. So here's a comparison slide. And what I'm doing is comparing the size of the Orion Nebula with the size of the Tarantula Nebula, and also contrasting its brightness. So as you look at this slide, you can see the Orion Tarantula Nebula on the right and the Orion Nebula on the left. And I actually had to scale up the brightness of the Tarantula Nebula and scale up the brightness, or scale down the brightness of the Tarantula Nebula and scale up the brightness of the Orion Nebula so you could see it. If I put it at the actual brightness comparison, you would not be able to see the Orion Nebula. But that little arrow there points to a tiny dot. That's the Orion Nebula. So it shows you how much more dominant the Tarantula Nebula is than the Orion Nebula, and how fortunate we are to be living in the part of our Milky Way galaxy, because as you look elsewhere along the spiral arms of our Milky Way galaxy, you can see much bigger and brighter star-forming giant molecular clouds. But we happen to be fortunate that, or blessed would be a better term, that we're living in this part of the local arm where there's no nearby big star-forming regions. Now, what about this local bubble? The local bubble is a region of underdense gas, dust, and stars. And there's a few of them in our Milky Way galaxy, but only a few. And we happen to be living right in the dead center of what's called the local bubble, a region where there's not much gas or dust. It's a very underdense region. And so we look at nearby stars. What we notice is there aren't any really big stars in our vicinity. Sirius is the closest big star, and it's not that big. And if you look at the stars in the region of our solar system, almost all of them are tiny dwarf stars. And so, because we live in this underdense region, we're not exposed to any gravitational disturbances or deadly radiation. And so, one of the reasons why we can have this class today, one of the reasons why human beings can live on planet Earth this day, is right now we're living in the center of the local bubble. So was that always the case? No, our solar system moves as it orbits around the center of the solar system. So we're not in the future going to be in the local bubble, but right now we are in the local bubble. In the past we weren't, but right now we're in the local bubble. Moreover, we're in dead center. Now, astronomers with their spectroscopes on board these giant telescopes are able to measure. Let's go back to this. Here we go. The periodic table. What they're able to do is actually look at different parts of our Milky Way galaxy and measure the abundances of these elements. And they're particularly interested in the abundance of the heavier elements. And what they notice is there's a gradient as you go from the center of our galaxy as you move to the outer edge. But it's not a linear gradient. So over decades, astronomers have carefully measured what is the abundance of these elements that are crucial for advanced civilization and for giving us the elements we need for human beings to exist. And what they've discovered is that it follows this interesting pattern as you go from the center of the galaxy out to the edge of the galaxy. So the center of the galaxy is not the region where you got the highest abundance of heavy elements. And there's a good reason for that. What our galaxy is doing is it's consuming, as we've mentioned in past lectures, these tiny dwarf galaxies. And they're being drawn into the core of our Milky Way galaxy. But these tiny dwarf galaxies have very few stars, but they got huge quantities of gas and dust. And most of that gas and dust is made up of hydrogen and helium. And so we actually have, at the center of our galaxy, an underdensity of heavy elements. But as you move away from the center of the galaxy, you've got these density waves taking gas and dust out where they're forming new stars. And at about 4 kiloparsecs from the center of the galaxy, we reach the maximum abundance in heavy elements. You say, well, what's a kiloparsec? It's 3,260 light years. I won't go into the technical details of why astronomers prefer the term parsec to light year. There's a reason why they do that. So if you want to translate that into light years, it works out to about 13,000 light years from the center of the galaxy. And so that's where you get a peak abundance. And again, because of the way the spiral arms are forming, we actually see it falling in abundance, and you reach a minimum at a little more than 8 kiloparsecs from the center of the galaxy. Then it goes up again, and then it drops way down as you go into the outer edge of our galaxy, where you go beyond the spiral arm structure. Now, what astronomers have recognized decades ago is that in order to get the heavy elements that we see here on planet Earth, we must have been born where we're at that maximum. So we had to be born at 4 kiloparsecs from the center of our galaxy, but we ended up at that minimum, at a little more than 8 kiloparsecs. So the first dotted line is where our solar system was born. The second dotted line is where we are right now. And so the question is, how do we get from 4 kiloparsecs out to a little more than 8 kiloparsecs? Well, I got two articles that are going to be released this Monday and 2 weeks from now that actually talk about the very latest research. This is not in the book, Design to the Core. It just got published literally weeks ago. But I got two articles coming out at reasons.org and my blog, Today's New Reason to Believe, basically new research on the birth cluster of our solar system, and recognizing that to explain the huge quantity of heavy elements we see in the sun, and also particularly in planet Earth, we had to be born in a very big cluster. Now, this would be the minimum size, and this is probably the more likely size. And so research is basically showing that the number of stars in the cluster in which our solar system was born was probably somewhere around 20,000 stars. 20,000 stars that are in this kind of a globular cluster thing that you see here in this slide, where the stars are close together, where you're going to have big stars exploding to be supernova, because some of the elements we see in the periodic table come from big supernova eruptions, others come from neutron star merging events. But in order to explain all the heavy elements that we see, we would have to be born in a cluster like this, where we'd be close enough to be enriched by the elements produced by core collapse supernova and neutron star merging events. Now, 4 kiloparsecs out from the center of the galaxy is a place where you actually do have these really big clusters. And so again, that kind of makes sense that we would be born there. And this is different because when I wrote Design to the Core, they were thinking, well, we had to be born in a cluster that had at least 2,000 stars. Some said 1,500 stars. That number's now gone up. It's not just 1,000 stars. It's 20,000 stars. So that's the new research that's come out. But then you got the situation, if we had stayed in that birth cluster, then we would have been subject throughout the last several billion years to deadly radiation, which might not have destroyed our solar system, but certainly would have made advanced life impossible in our solar system. And, we're not there now. Here we are, a little more than 8 kiloparsecs from the center of the galaxy. And so we must have gotten ejected from our birth cluster, and then we wind up where we are now. Say, well, how would you get ejected? We would get ejected in the same way that when NASA wants to go to Uranus or Neptune or Saturn, they look for a gravitational slingshot. You say, what's a gravitational slingshot? Well, in order to save money on getting our spaceships to these distant planets in our solar system, they'll often send a spacecraft and it'll orbit Venus first and get a big push from Venus, a gravitational push, which sends it out. They get another push from Jupiter, which sends it out. So they actually look for these gravitational interactions, and they carefully calculate it on their computers as to what kind of gravitational pull or push you're going to get. And so this is all the way NASA gets these expensive spacecraft to these distant planets that they want to observe. They basically save a ton of your tax dollar money by using planets like Venus and Mars and Jupiter, but especially Venus and Jupiter, as gravitational slingshots to take it out to where they want to go. They're able to get it there faster. So, for example, if you wanted to go to Mars, you can actually get there with existing technology in 5 or 6 months. But you can only get there in 5 or 6 months if you send the spaceship at just the right time, at just the right trajectory to get a gravitational slingshot to get you there faster. Without the gravitational slingshot, you're looking at about 2 years to get to Mars. But with the gravitational slingshot, you can speed it up, and you're going to use a lot less fuel to get there. Now, to get a gravitational slingshot to kick the solar system out of its birth cluster, you would need a gravitational slingshot generated by at least 4 massive stars. So it means that the solar system, when it was forming, was in a position within its birth cluster where there were 4 or more massive stars that gravitationally worked together to slingshot the solar system out of the birth cluster. And it would have to be a strong slingshot to send it as far away as 8 kiloparsecs from the center of our galaxy. And so this basically shows you, this next slide, how this works. It shows you where the sun was in an area where there's a very high population of star clusters and gaseous nebulae, a very dangerous spot for life. And then we wound up being slung out to where we are now. Now, there's actually 2 gravitational slingshots you need. One to eject the solar system out from its birth cluster, then you need a second one to stop it. You got to put the brakes on the thing. Otherwise, we just keep going out. And so what happened is when we got to this favorable location at a little more than 8 kiloparsecs, the solar system encountered another set of massive stars that slowed down and braked the movement of the solar system. And so we were literally ejected from the most dangerous part for advanced life, or any kind of life, in our Milky Way galaxy, and we got stopped in the ideal location for advanced life. So we went from the worst spot to the best spot thanks to these 2 different gravitational interactions that occurred. Now, I'm out of time, but what I'm going to share with you next week is the significance of that red annulus. What's going on with that red annulus? It turns out the only place where advanced life is possible is at the inside edge of that red annulus. So again, it shows you the fine-tuning that is necessary, namely that we have to be ejected from the birth cluster, but we got to be stopped exactly at the inside edge of that red annulus. So we'll stop there, and we'll take questions. And as usual, we're going to alternate between people that are here in person and people that are participating online. So it looks like we got an online question first. And do I need to turn my microphone off, or are you going to control it back there? You got it back there? Great, thank you.
Here's a question from Robert Gibson online. I have just read about the JWST has viewed some baby galaxies which are less than 400 million light years old. What is the latest information on these baby galaxies, and how important is this discovery?
Okay, he's referring to the James Webb Space Telescope. And the James Webb Space Telescope's primary mission is to actually determine what is the details of the early history of our universe. And so it's a powerful infrared telescope. They purposely put it infrared because if you're looking far away, the light is red-shifted into the infrared part of the spectrum. And so that way they were able to get higher sensitivity. Of course, it's a big telescope. And so for the past year, its primary mission has been looking at the galaxies in the very distant part of the universe, which means in the very early history of the universe. And so they're looking at these baby galaxies. Now, before the James Webb Space Telescope went up, the thinking was it's going to take significant time for galaxies to form in the early history of the universe, and then these galaxies will actually get bigger and bigger as they merge together to make bigger galaxies. The initial images that came out, you've probably heard stories. It was on the internet saying these baby galaxies are too bright and too big. The Big Bang creation model tells us that these galaxies should be relatively rare in the early history of the universe. And a year ago, when this was first coming out, I put out articles on my Facebook page. I've written 3 articles as part of my Today's New Reason to Believe, making the point that, of course, the James Webb Space Telescope, they're going to first do short exposures on these distant galaxies. And which galaxies are they going to see? They're going to see the big bright ones. So it's not at all surprising that they first found the big bright ones. They're the easiest ones to see. To actually get a true picture of what's happening in the early universe, you need to be able to image the entire population of baby galaxies. 2 images, only 2, have been done where the observing time is more than 15 hours. But both of them show that indeed the faint small galaxies far outnumber the big bright galaxies in the early universe. And I posted an image on my Facebook page as well as in one of those articles that I wrote, basically showing you a single image which shows a handful of big bright galaxies in the early universe, but 50,000 faint small ones. And so the Big Bang model has been proven correct. The small faint ones far outnumber the big bright ones. And that was one of the missions of the James Webb Space Telescope. We've got dozens of Big Bang creation models. Where they differ from one another the most is what's happening in the first 4 billion years of the universe. So the James Webb Space Telescope eventually will tell us which of those dozens of Big Bang creation models really does correctly describe the early history of the universe. And I'm in the process right now of writing an article, it'll come out sometime in November, about the latest James Webb Space Telescope discovery that the first stars in the universe, when they explode, do not make the quantity of heavy elements that we used to think that they would make. And so the early universe seems to be underdense in heavy elements manufactured by supernova eruptions. And this actually makes all the more extraordinary that we have all these elements here on planet Earth that we see in the periodic table. Because the thinking was the first generation of stars makes a lot of these heavy elements, and they get incorporated into the second generation of stars, which make even more of these heavy elements, which actually plays a role in stars like our sun, which are third generation stars. But now it becomes more challenging to explain the huge abundance of heavy elements in the sun and the solar system, because we now have evidence from the James Webb Space Telescope that these first stars are nowhere near as efficient in making heavy elements as we used to think. You say, well, how come they didn't know? Well, one of the missions of the James Webb Space Telescope is to determine the population demographics of these firstborn stars. Are they predominantly small stars? Are they predominantly big stars? What's the upper limit on the mass of these first stars? Because the first stars are going to be made up of just hydrogen and helium. But there's been a big debate amongst astronomers. Stars that form from only hydrogen and helium and a trace amount of lithium that's made in the Big Bang creation event, what are those stars going to be like? And that's what's actually going to shed light. In fact, this discovery that we see this underdensity of heavy elements is actually going to give us some insight on what those first stars are really like. I'll try to keep you posted.
Well, you just answered half my question. I was going to ask about, I know you're going to do a series on the uniqueness of our sun, and the general theory is that a third generation sun. So the part of my question that didn't get answered is the cluster that our sun was born in, would all the stars in that cluster be third generation stars then? And how old was that cluster? Was that cluster came later because it had to be third generation material?
Yeah, if I could go back to this image here. Given that our star was born in a cluster that had like 20,000 member stars that are all close together, we've done a lot of research, we astronomers, on the 152 globular clusters that populate our Milky Way galaxy. And they all have different ages. But it turns out that there's not much of an age spread in the stars that are part of a particular cluster of this size. So to answer your question, the vast majority of stars in the solar system's birth cluster would all be approximately born at the same time. Now, when I say at the same time, I mean, hey, relative to a universe that's 14 billion years old, they're all probably born within a window of about 200 million years. So they're all roughly the same age. So now you had a follow-up? That's it? Okay, good. Okay.
We have a question from the internet. I don't know.
No. I was going to let Doug. Doug's going to do his question.
I thought Valerie was online again. Well, I was going to ask about why the moon doesn't really have plates, but you got me really interested with this Milky Way galaxy graphic thing. Can you go back to that slide that you had up just a little while ago with the Milky Way, sir?
Which one?
The previous slide you had. Yeah,
that
okay.
one?
So obviously you said this isn't an image that was taken from a spacecraft of any kind, but I've always wondered about the Milky Way galaxy because I've seen these kind of representations in books and things. It almost looks like it's like a disk, like you would think that it would just be like a ball of stars, with gravity. Why is it kind of flat like that a little bit?
Well, yeah, spiral galaxies are dominated by this flat stellar disk, and you say what's generating the disk is the rotation. So it's rotating and it kind of spreads things out along a disk, and it's because of the size of it. Now you do see most of the galaxies in the nearby universe are spheroidal galaxies or ellipsoidal galaxies where they don't have a disk shape and they look more like a giant ball of stars and gas. And many of them are the result of a disk galaxy collapsing, where the spiral structure collapses and all the stars rush together and they become like a ball. And if you look in the center of our galaxy, you'll see that there's a bar there. Well, it's several spiral galaxies. Let me actually see if I can get you back to a slide that shows you other spiral galaxies. Here we go. Okay, spiral galaxies come in two categories, those that have a central bar and those that have a central bulge. And some of these here are more bulge-like. And what you notice is there you've got in the core of the spiral galaxy kind of something like a basketball shape of stars, then extending out from that as a disk. So when the spiral structure collapses, it basically collapses into that core and it becomes like a football shape or it becomes a basketball shape. But yeah, wherever you see a disk is where the stars are spread out. And it's the rotation that generates that.
It appears in the image that it's rotating. Say you were that far enough you could see it or somehow see this. What causes that to rotate? I know you're going to probably say gravity, but is inertia involved, or is
Well,
it
it's a
slowing down, or?
Yeah, it's a conservation of angular momentum, which is generated. So, for example, you notice that the planets are revolving around our star, the sun. And, that's just the conservation, because as the gas cloud from which the solar system formed collapses, it causes the system to rotate more rapidly. It's the figure skater effect. You've ever seen these figure skaters rotate very rapidly in their exercises? What they do is they extend their arms and their legs out like this. And that way they got lots of mass far away. And then they gradually bring their legs together and their arms together. And so they start a slow spin out here. So they spin like this, and as they pull in like this, it spins up. And so it spins very rapidly as they pull the mass together. That explains the rotation of the sun. It explains the revolution of the planets around the sun. It explains the rotation rate of all the planets. It's simply the conservation of angular momentum. So, for example, going back to our Milky Way galaxy, let me pull that up again for you. The way that works, and this is basically Newton's laws of motion, that's part of where the angular momentum comes from, is that the closer you get to the center of the galaxy, the faster you revolve around the center of the galaxy. And so the stars that are, say, at the top of that image, they will take more than 1 billion years to make one revolution around the center of the galaxy. Where our sun is located, it takes 250 million years to make one revolution around the center of the galaxy. Now, the stars that are in the center of the galaxy, it only takes a few tens of millions of years for them to make one trip around the center of the galaxy. And stars that are close to the supermassive black hole, we're talking just thousands of years to make a trip around the center of our galaxy. And it's the same principle in our solar system. Mercury goes around the sun about 4 times faster than the Earth because of how close it is to the sun.
Okay. Here's a question from Valerie. I've been hearing on Christian videos that the time dilation hypothesis of Barry Satterfield is back. It posits that the speed of light has decreased over time, thus the universe is not old, but is consistent with the young Earth concept. Could you please comment? There's another
Yes.
question that goes with it. I'll give it to you in a minute.
Okay, Barry Satterfield is an Australian. He recently passed away, but decades ago he made the claim as a young Earth creationist that we got no problem with light getting to us from distant stars and galaxies because in the past the velocity of light was much faster than it is today. And what he did is he cited 2 sources of evidence for why he believed the velocity of light was faster. One is that he appealed to the measurement made by the Danish astronomer Romer. 300 years ago, he measured the velocity of light by looking at the satellites that revolve around Jupiter and timing them. I won't go into the technical details of how that relates to the velocity of light, but he came up with a measurement that was 1% greater than what people measure here on Earth today with modern equipment. And so what Barry Satterfield did is he took Romer's measurement of 1% greater than what it is today, took the modern measurement, and he extrapolated an exponential curve through that back to the time of Adam, whom he presumed was created as 6,000 years ago, and said at the time of Adam, the velocity of light would be about 1,000,000 times faster than it is today, and that would explain how distant starlight and distant galaxy light could get to our telescopes in just thousands of years instead of billions of years. Now, the second data point he cited is he made a claim that he had a dream in the middle of the night, and it was Jesus that visited him and told him that the velocity of light was faster in the past than it is today. Which, from my perspective, I would cite first, Peter or 1 John, who says, "Test the spirits." Not everybody that appears as Jesus really is Jesus. But, and Barry is not a scientist. He does have I respond in detail to Barry Satterfield in my book, A Matter of Days, the second edition. I do list his educational qualifications. He and a fellow, Norman Trevor, I think Norman Trevor actually has a bachelor's degree in math. Barry Satterfield, no. But they published, about a 75-page paper in which they detailed their claims that the velocity of light was exponentially faster in the past. Now, what they don't reveal in their paper or in their public claims is, yes, Romer did measure the velocity of light to be 1% higher than it is today. It's also true that subsequent measurements of the velocity of light were also a little bit higher than the modern value. Not as high as Romer's, but they got down to 0.5% higher, 0.25% higher, etc. What Barry and Norman and Trevor failed to reveal is that the error bars were far greater than the claimed effect. So if you look at Romer's measurement 300 years ago, yes, it was 1% above the modern value, but the error bar, the measuring accuracy, was plus or minus 3%. So the measuring error was much greater than the claimed effect, which scientists always say, you didn't prove anything. If your measurement is less than your error bar, you've got no evidence. So now, what I did put in A Matter of Days, we know from 3 different reasons why Barry Satterfield has to be wrong about the velocity of light being faster in the past than it is today. Number 1, the Bible tells us that the laws of physics do not change. They have not changed since God created the universe, and they will not change until the full number of humans that God intends to redeem have been redeemed. The velocity of light ties very intimately into the constants and laws of physics. So you got the Bible repeatedly declaring there's been no change in the physics of the universe, which means there's no change in the velocity of light. Number 2, we astronomers measure the velocity of light every time we look at a distant star or distant galaxy, because we see what are called Zeeman split lines. Now, if you've taken basic chemistry, you know what I'm talking about. If you haven't, there are certain spectral lines that physicists and astronomers look at where a single line gets split into 2 lines. The degree of splitting depends on the velocity of light. And so one of the easiest Zeeman split lines to measure is neutral hydrogen. And it's, hydrogen is the most abundant atom or element in the universe, so we can measure the Zeeman splitting effect of that neutral hydrogen line all the way out to 13 billion light years away. We see it in stars, we see it in galaxies. As we look at the splitting of the lines, we see it doesn't change. It's the same everywhere. And so that is evidence that the velocity of light did not change in the past, because if we look at the Andromeda galaxy, 2.5 million light years away, which would imply if there's no change in the velocity of light, it's 2.5 million light years away. It took that long for the light to reach us, but the velocity of light that we measure in the Andromeda galaxy is identical what we measure in the lab today. That's true all the way out to galaxies that are 13 billion light years away. Reason number 3, there's more reasons, but I'm going to stop at 3. Reason number 3, we know the velocity of light can't be different, because if it was faster for Adam than it was for us, Adam would have been incinerated by the heat of the sun. You say, how can you make that claim? the one equation that every person almost in the entire world knows, E equals mc squared. E is for energy, m is for matter, c is for the velocity of light. And notice it's squared. And so if the velocity of light were 1,000,000 times faster for Adam than it was for us, the heat and light of the sun would be 1,000,000,000,000 times greater than it is for us today. So you can imagine how warm it must have been in the Garden of Eden if the heat of the sun was 1,000,000,000 times greater than it is for us today. And the biblical text is quite clear. Adam did not get incinerated. The earth did not get incinerated. So those are three, I think, compelling reasons why the claims from Barry Setterfield and Norman Trevor have to be wrong. Now, to their credit, there are young earth creationist organizations today who have backed away from that and said, this is not a good reason why for a young earth creationist model. But I think if they were fully honest, they would say the fact that the velocity of light has not changed means we have to be wrong about the age of the earth and the age of the universe. It's not just a bad argument on their part. The argument is actually a compelling counter that disproves the young earth creationist model. Okay, next question.
There was a follow-up, but I think you answered it. It's from Hank Bellows. Can we actually know whether the speed of light has always been constant? So you've answered that. Now, Mary Ann, she has a question.
Hello, Dr. Ross. Thank you so much for your teaching and everything that you help us to understand. My question is about the chosen and the episodes, the seasons.
Yes.
Okay, I haven't seen the movie yet.
Oh, I know what you're talking about. It's a series.
Yes.
Yeah. Okay.
You know, in the seasons, they show the stories in the Bible, and some of those stories are extended, I guess I could say. So I was wondering how much of that is it just to like fashion the story to help us understand what happened at that time for that person?
Yeah, well, I've watched the first 3 seasons of The Chosen. I personally recommend it because it really gives you a good feel of the emotional impact of the ministry of Jesus when he was here on earth. And what the writers of The Chosen are doing is trying to create the drama as if it was happening in real time. And so it's not exactly like what you see in the gospel accounts. Because the gospel accounts are giving us a summary, is giving us a few isolated details. And in order to make this a living drama, they had to fill it in. Now, the writers of The Chosen are very upfront saying, this is what we're doing. We're not claiming that everything you see in The Chosen is exactly what happened, but we're trying to portray the impact of what Jesus' ministry would have had on people in real time. And so they will add some fictional elements, and they'll add some personal engagements, but also in order that it not be a 15-year series, they actually blend some of the stories in the Gospels together. And so as you look at it, you say, wait a minute, that's not the chronology that I see in Scripture. And that's 2 separate events, not one event. Well, they're blending them in order that they don't have to have the series extend forever. So I think they're looking at 8 series altogether to tell the whole story. But they said, yeah, to make it only 8 series, we had to blend some of the stories together. So yeah, but they're very careful with the disclaimers. But I think they've done a decent job of approximating probably what it was like for people that were experiencing it in real time. And yeah, it has a dramatic emotional impact on people that watch it. And you get a real flavor of what it was like to be one of the disciples, or what it was like to have an encounter with Jesus. They also make it clear we can't portray the drama as dramatically as it really was. I actually got to talk to the producer, and he said, you know, our greatest difficulty was trying to figure out how we can put on film Jesus walking on the water or Jesus calming the storm. And they pulled it off, but he also said, it was way more dramatic than what we showed in the film. And so, as dramatic as it is, the drama is a whole lot less than what it would really have happened. But again, I recommend it. It was a blessing for me to watch it. But do recognize the disclaimers.
Some parts of it, it does bring me to tears, so I understand. Thank you.
Hugh, we have a question from Ron Kokanovich. How would you suggest one handle the credibility of Muhammad riding a flying horse to heaven?
What about Muhammad's claim of riding a horse to heaven? You actually have in the gospel accounts Jesus being ascended from earth up into heaven while the disciples are watching them. And so I'm not surprised that we see in the religion of Islam a similar story of Muhammad being taken up on a horse. Interesting contrast, because the Bible portrays Jesus coming to Jerusalem on a donkey. The book of Revelation portrays him coming back on a horse. The symbolism is significant. The donkey is a symbol of peace. The horse is a symbol of conquest. And so the Christian message is one of Jesus first coming as a servant in peace to sacrifice himself for the sins of the world. When he comes back again, he'll come as a conqueror to do away with all sin and evil. But in Islam, you got Muhammad coming as someone on a horse to conquer, and that's the birth of Islam. The birth of Islam is armies going throughout the Middle East and Europe and Asia and conquering people and subjecting them to Islam. Notice how different that is from the Christian message. It's one of Christians under severe persecution, going throughout the Roman world, the Parthian Empire, India, and beyond, but under great persecution, they were able to spread the message. They didn't go out to conquer, they conquered people through spiritual means rather than physical means. I'm going to stop there because I know this is going to get back to my Islamic friends.
Okay, Nancy has a question. Get real close.
Is that close enough? He said get real close. Just a comment related to the question about The Chosen. I'm with the Jesus Film Project. Some of you know that. And just if anybody's interested, I have copies of that with me. It's a different concept. It's straight from the literal text of the book of Luke in over 2,000 languages now. So the cards I have, you can pull up any of those 2,000 languages and pass it on to somebody that might speak one of those languages. But talk to me afterwards about that if you like. But my question is related to William Lane Craig. A group of us got into a discussion the other night about evolution came up, and some were convinced that William Lane Craig is an evolutionist. I said, I don't think so. I had him as a professor down at Biola University, but not sure how people are coming to that conclusion or any evidence that they're giving related to that. Thank you.
All right. Well, I've known Bill for over 35 years, and where this is coming from, Nancy, is he published a book almost 500 pages long, or 2/3 of it is footnotes in very tiny type. The book is called In Quest of the Historical Adam. And there he proposes that Adam lived about 750,000 to 1 million years ago. And therefore, people have looked at his model and says this is very similar to what evolutionists say about the history of humanity. So in Bill's model, you've got Neanderthals as part of the descendants of Adam and Eve, and he claims that these early humans, of Adam, were evolving over time into what we see today. Now, I've written a book that responds to Bill Craig's In Quest of the Historical Adam. It'll be actually released tomorrow. The book is called Rescuing Inerrancy, A Scientific Defense. And so we're releasing it to our donors tomorrow, and we're going to do a general release probably somewhere in late November or December. But Bill got an advanced copy of the manuscript while it was still being edited. And so I got a letter from him saying, Hugh, that was a thought experiment. it wasn't a model. And so I sent an email back to Bill saying, well, I'm familiar as a scientist with thought experiments. Thought experiments where you basically tell people up front, this is not a model, this is simply a thought experiment to say what if. And it says in science, thought experiments typically run no more than 3 pages. And you repeatedly say throughout the piece, this is a thought experiment. I said, Bill, you shouldn't be surprised if people read your book and assumed you were presenting a model, because look at how long it is. Almost 500 words, and it's a lot of, look at all this small type. By the way, in my opinion, the most valuable part of Bill's book are the footnotes, because he basically surveys what people have thought over the centuries, and particularly in modern days, about human origins. So a lot of good material in the footnotes. But the regular type basically is his position on human origins. Now, what I did do in my book, Rescuing Inerrancy, is I published Bill's latest position, because he says, you know what, the way this is portrayed, it makes it look like I don't believe in biblical inerrancy, or that I'm adopting naturalistic evolution. And I says, well, Bill, I'm okay with you changing your mind. And so, if you wanted me to write a statement about where you stand right now, so I basically did put in Rescuing Inerrancy, Bill's request, hey, this was only a thought experiment, it was not a model, and I do believe in biblical inerrancy as is defined by the International Council of Biblical Inerrancy, but only the 1978 statements. He clearly denies the hermeneutic statements. And so I basically, put his quote in there as he requested it, but I made it very clear. While he does make a case for the doctrinal statements, the International Council of Biblical Inerrancy, he clearly denies the hermeneutical statements. And you say, well, which one in particular? Well, the one he denies is that as we read the first 11 chapters of Genesis, this is literal history. He does not see it as literal history. He calls it mytho-history. And he basically says it's predominantly myth, but there's some historical truth in the text. And he's also explicit in what he believes not to be true. And that would be the tree of life and the tree of the knowledge of good and evil, the cherubim. He calls them fantastical elements, things that can't be true if the text is read as literal history. And that would include the flood, the size of the ark. I mean, he's got a list of about a dozen things in Genesis 1 to 11 that he would label as fantastical elements. And I respond to that as well in the book that will be released tomorrow, basically saying the entire Bible is filled with fantastical elements. Jesus walking in water is a fantastical element. That axe head that floats up to the top of the water, that's a fantastical element. And moreover, I think some of his fantastical elements, particularly those that pertain to the flood, even the way Bill interprets it, I don't think they're fantastical elements. Those are things that could be naturally explained. So, for example, the fact that the ark is so big. Well, the Bible doesn't tell us how long Noah took to build the ark, but it could be as much as 100 years. And so if he was taking decades to build the ark and he was able to hire a lot of people to help him, I don't think the ark is beyond the engineering capabilities of Noah and the people of his generation. But yeah, Bill is not alone. Lots of theologians have said that's physically impossible. That's got to be hyperbole. And Bill's comment is that when you look at the flood text, for example, he does agree that some of it is hyperbolic, but he says it's not just hyperbole, it's hyperbole plus myth. So now, I am thinking that Bill may be moving back towards the positions he held decades ago. The fact that I actually saw some movement in the email exchange with him, and I'm more than willing to have people change their minds on issues. But I do wish he had stated that this was a thought experiment. But no one publishes a thought experiment this 500 pages long. But that's kind of where Bill and I stand on that issue.
Okay. Question from Jan Pukowski, how do we know the universe is not infinite when everything we see is only the observable universe?
Well, we don't know. And so the universe we see through telescopes is the universe of the past, and the universe is expanding. So the universe we see in telescopes only goes out to 13.8 billion years, because that's the age of the universe. But given that the universe has been expanding throughout those 13.8 billion years, we know at a minimum the universe today must be 94 billion light years across. Whereas if all you look at is through the telescope, you get maybe 27 light years across. But because of expansion, it's bigger. Now the question is, how much bigger? Well, to know how much bigger the universe is than 94 billion light years, we need to know with precision the geometry of the universe. And it's been measured to almost 4 places of the decimal, and that measurement tells us it looks like it's approximately flat. Now, if it's approximately flat, it could be a finite size, or it could be an infinite size. Now, we're talking infinite in space, and we're talking the space-time dimensions being infinite, not necessarily the matter and the energy in the universe being infinite. And of course, it's not infinitely old. It's only 13.8 billion years old. So it's finite in time, but if the geometry of the universe is hyperbolic or perfectly flat, then the lines of space go out to infinity. And a good analogy would be thinking of an ellipse. With an ellipse, the lines don't go out to infinity, but with a parabola, the lines of a parabola go out to infinity. And so, but we're talking the space dimensions.
It's really interesting this subject came up because I've been reading about this thing called it's ERIDANUS, supervoid. It's like some kind of hypothetical evidence that people, or some authors have said, is evidence for a multiverse. Is that just theoretical? Have you heard of that?
Yeah, you better tell me again what that is. I couldn't quite.
I can't pronounce it.
Well, can you spell?
Eridanus.
Pardon me? You put the microphone closer to you.
What is it? ERIDANUS.
Ah, that's a version of what's called the M theory. And in M theory, you got physicists that speculate that you got length, width, height, and time. And we know there are 6 other very tiny space dimensions, but M theory posits there's extra big dimensions of space. Now, there's no scientific evidence for it. There's no scientific evidence against it. Moreover, there never will be evidence for it or against it. But with M theory, you got the possibility that there could be other big space-time realms. But it's an hypothesis without any observational support for it or against it. I mean, it was Einstein who made the point. Once you got observers in a universe, those observers are only able to observe what's in their universe. They can't observe what's beyond the universe. Just like we can't use our telescopes to peer into the angelic realm, we can't use our telescopes to peer beyond the space-time surface of the universe. But you are free to speculate what exists beyond the universe.
I think that's all the questions, Hugh, so if you'll close us in prayer.
Yeah, happy to do that. Father in heaven, we thank you for this day. Thank you for every day you give us to serve you here on planet Earth. And we'll look forward to the time when we can serve you in the new creation, where all the restrictions of this physical realm will be delivered. But we thank you, Father, that you're on a quest first to eliminate all evil and suffering. And thank you, Lord, for the privilege of being able to see you, to worship you, and to serve you. In Jesus' name, amen. Thank you.